This is the first section that we're going to look at on exponential functions. We're going to have actually a couple of them. This is the first one, and if you'll look at the top of your notes, we're going to look at a definition of exponential function. It says it's a function of the form f of x equals a to the x, where a is a positive real number. A has to be greater than 0. That means positive real number. And it can't be 1. So let's look at a couple questions now about that definition. First off, why does a have to be greater than 0? Think about it. If a was a negative number, let's say a was negative 2, so that it wasn't greater than 0, there would be values of a to the x that would be undefined. Can you think of one? How about negative 2 to the 1/2? That means square root of negative 2, and that's not defined. Therefore, a must be greater than 0. We can't have the base a be negative numbers. So that's a real important thing to remember. The base can't be negative numbers. It has to be greater than 0. All right, why does a have to not equal 1? Well, think about it. What if a did equal 1? 1 to any power is just 1. So then what you would have would be a constant function, and no longer would it be exponential. So those are the two limitations on the a. Now, it's real important here. You'll see in your notes a star, and it says note. It's important to look at the difference between a power function like g of x equals x to some power, where that power is greater than or equal to 2. That's different than an exponential function where the x is the exponent. Here, in the first one, in the power function, the x is the base. In the exponential function, the x is the exponent. And that's something that we haven't done before. So we're going to do an exploration. You're going to need your graphing calculator. So if you would, go into y sub 1, or y equals, clear whatever's there, and I want you to put in 2 raised to the x power. And as far as a window goes, let's just click on the button that says zoom, and we're going to pick number 6, zoom standard. Now it's a little bit small, but you can actually see pretty well. When you put in y sub 1 equals 2 to the x, you get a graph that looks, I'm going to make it a little bit bigger than what it is on that screen that you have, a graph that looks something like this. And it goes through that point 0, 1. Now we're going to complete this chart. So in your notes you'll see a chart that has x, y, and then something that looks complicated but isn't. It says f of x plus 1 divided by f of x. All that means is second y divided by first y, and I'll show you in just a second what that means. The notation looks kind of scary, but it really is quite easy. So I've already listed the x's I want you to try. So if x is negative 2, what would y be? Well, if x was negative 2, then we would have y sub 1 equals 2 to the negative 2. Negative exponents mean reciprocals, so that would be 1 over 2 to the positive 2, or 1/4. And I'm going to show it as a decimal just because it's going to be a little bit easier, 0.25. Now let's do negative 1. Y sub 1 would be 2 to the negative 1, which would just be 1 over 2 to the first, or 1/2. Again, I'm showing it as a decimal. 0. 2 to the 0 is 1. Anything to the 0 is 1. If x is 1, you would have 2 to the 1, which is just 2. If x is 2, you would have 2 to the second power. Remember, the x is the exponent, which gives you 4. Raised to the third power, you have 8. Okay, you see what we're doing. Raised to the fourth power, you have 16, and to the fifth power, you have 32. Now I want to show you something interesting about exponential functions that is not true of other functions. Now we're going to do this third column. That means take the second one and divide it by the first one. So in this case it would be the 0.5 divided by 0.25. Well, if you do that on your calculator, you'll see that you get an answer of 2. All right? For this next spot, we're going to take this one, 1, and we're going to divide it by 0.5, the one that came before. So we're taking a second one each time and dividing it by the one that came before. You get 2. Go to this next spot, and we're going to take this one and divide it by the one that came before, and you still get 2. And in fact, we could continue that throughout the entire chart, taking a second one and dividing it by the one that came before, and what you see is you always get a constant value, and we're going to call that constant value A. So you'll see a theorem there, and it says for an exponential function only, if f of x equals some number to the x power, then f of x plus 1 over f of x equals A. Notice our A here was our 2. The base in our original function right here, the base. If it had been a 3 when we did this, we would have gotten 3 for our A. So that's something kind of unusual about exponential functions. All right, so let's go to example 1. It says sketch the exponential function f of x equals 2 to the x. Well, I already did that right up here, and I'm going to continue to use that one. It says from the previous exploration, on the same grid, I want you to graph g of x equals 3 to the x, h of x equals 4 to the x, k to the x equals 6 to the x. All right, so go into your calculator. We're going to change this window. Let's change it to match the picture that I sketched and the picture, the coordinate plane that's on your grid. Let's go from -3 to 3 for the x with a scale of 1. For the y, let's go -1, 2, 3, 4, 5, 6 to 6 with a scale of 1. And go ahead and put that first graph back on there, and you'll see it looks very much like the one I did, only you can see it more zoomed in. Now I want you to go to y equals, and I want you to type, hit enter for that one, and then go down to y2, and I want you to put 3 raised to the x power. Okay? Hit enter, and then I want you to do 4 raised to the x power. Hit enter, and finally for y sub 4 I want you to put 6 raised to the x power, and then when you hit graph, watch your graph very carefully about which one comes first. So go, hit graph, there's your first one. Your second one should start below it, but then go inside it. Third one starts below it, goes inside. Next one starts below it and goes inside. In fact, it gets very crowded. It's actually hard to see, but it looks like this. This was 2 to the x. The next one starts like this, goes through that same point. This is 3 to the x. The next one starts inside it, goes through that same point. This is 4 to the x. I don't have room to put on 6 to the x. But notice something. They all go through that point, 0, 1. So now what we're going to do is we're going to complete the table that we have here, where we are comparing g of x, which is 3 to the x, to h of x, which is 4 to the x, and k of x, which is 6 to the x. I didn't put 2 to the x on there. I guess I should have. So if x is -1, g of x would be 3 to the -1, which is 1/3. H of x would be 4 to the -1, which is 1/4. And k of x would be 6 to the -1, which is 1/6. You see what we're doing? All right, if x is 0, you would have 3 to the 0, which is 1, 4 to the 0, which is 1, and 6 to the 0, which is 1. And that answers our question about why the point 0, 1 is on all of the graphs that we did. 0, 1, 0, 1, 0, 1. It's on all of those points. Those points are on all those functions. Let's do 2. Then we would have 3. Oops, I missed 1, didn't I? Sorry. Let's do 1, x being 1. 3 to the first is 3. 4 to the first is 4. 6 to the first is 6. Okay, if x is 2, we would have 3 squared is 9. 4 squared is 16. 6 squared is 36, and so on. You could complete the chart if you want. So we see that there are points on the graph of those functions that they have in common, the 1 point, 0, 1, but the graphs are related in that they're the same shape, basically, but as the number gets bigger, as your base gets bigger, the graph gets steeper. So let's look at example 2, and it says graph the exponential function f of x equals, now we're going to change it, we're going to do 1/2 to the x power. Up to now, we've had our base be whole numbers. Now we're going to use a rational number. So I want you to go back into your calculator, go to y equals, clear out all those graphs, think about what they look like. You should have a sketch there in your notes. And I want you to type y sub 1 equals, and you're going to have to use parentheses, 1 divided by 2, close parentheses, raised to the x power. And now I want you to hit graph on that same window. And look at how that it is related. Here is f of x equals 2 to the x. We know that it looks like this, where it goes through that point 0, 1. But when you did f of x equals 1/2 to the x, we ended up with a graph that looks like this. So it's similar to f of x equals 2 to the x, but it has been rotated across the y-axis, or reflected across that y-axis. But notice, it still goes through the point 0, 1. There's a little chart there. We're not going to do the whole chart, but I want to just kind of do a couple of these so you see how this works. If x is negative 10, we would have 1/2 to the negative 10, which means the reciprocal, which means 2 to the 10, which is 1024. If we had negative 3, you would have 1/2 to the negative 3, which is 2 to the positive 3, which is 8. If it's negative 2, you have 1/2 to the negative 2, which would be 2 to the positive 2, because remember the negative reciprocal, the negative exponent means use the reciprocal, which is 4. By the way, don't get confused here. We can't have our base be negative, but we can definitely have our exponent, our x, be negative. Negative 1 is 1/2 to the negative 1, which is 2 to the 1, which is 2. We could continue to the 0 power. We would have 1/2 to the 0, which is 1. To the first power, we would have 1/2 to the first, which is 1/2, etc. You can finish filling that in. So there are points on this graph. Let's look at this point. We have the point negative 1, 2. And we have the point, I want to look at this point, 1, 1/2. Where on our first graph, 2 to the x, if you look back at the chart that you have there, you have the point negative 1, 1/2. Oops, negative 1, 1/2. But then you have the point 1, 2, which is right here. 1, 2. Notice how they're related. The 2. We've got negative 1, 1/2 here. Over on this one, I have negative 1, 2. Here on this one, I have 1, 1/2, whereas on 2 to the x, I have 1, 2. So they are related. It's just a reflection, again, across that y-axis. All right, so let's kind of summarize here. It says graphs of exponential functions are classified into two groups depending on the base. So we have f of x equals a to the x, where a is greater than 1, so it's not a fraction. And then we have f of x equals a to the x, where a is between 0 and 1, meaning it is a fraction. So here's a fraction, and this is an integer, a whole number actually, not an integer because it can't be negative. A whole number. I said integer and wrote integer. Alright, so let's look at how their graphs are different. Again, just in summary, we know that when you have any base raised to the x power, it's going to look like this. And how steep it is depends on the base, but it's always going to go through that point 0, 1. When it's a fraction, when your base is a fraction, it's still going to go through that point 0, 1, but it's going to look like this. It goes the other direction. Alright, so let's go to example 3. It says graph f of x equals 2 to the negative x minus 3 using transformation. So here we are back at transformations again. And let's look at, and I want you to do this without your graphing calculator. So let's look at what this looks like. We're going to start with our parent function. So the parent function is just y equals 2 to the x, and we know it goes through this point. And since the base is a whole number, it goes something like that. I'm not going to do it exactly. We know that we have the point 1, 2, and we know we have the point 0, 1, and negative 1, 1/2. We know we have those points, 0, 1. All right? Now, from here, we are going to replace the x with negative x. And think about what that does. What that does is it's going to flip it across the y-axis, just like it did with any other transformation. And so what we're going to get is it flipped across the y-axis like this. Alright, still goes through the point 0, 1. And this function is y equals 2 to the negative x. So the x became negative. Now this last piece right here, that's just a vertical shift down 3, just like it was with any other kind of transformation function. So from 0, 1, instead of being there, it's going to be down 1, 2, 3. So what is it? Where is it going to be? It's going to be at 0, negative 2. So it's going to kind of go like this. And I didn't really sketch that very well. But if you do that, you're going to see that there is a line down here at y equals negative 3 that is a horizontal asymptote. It can't ever touch there, just like it doesn't ever touch the x-axis prior when we did it before we transformed it down. Now, if you want to put those in your calculator, you can test them and you'll see if we did it correctly. So go to y equals, hit clear, and let's do 2 to the x power as our y sub 1, hit enter, and then do 2 raised to the, use your negative sign, not your takeaway, negative x, hit enter. And now do 2 raised to the negative x and then minus 3. And we may have to put the negative x in parentheses, I'm thinking. 2 raised to the, I'm going to put mine in parentheses so that it doesn't, I don't know how this is going to work. You may have to play with that. I don't know if it's going to think that it's raised to the x minus 3 or if the minus 3 comes on the end. So now I want you to graph those. Probably have to change our window. Your first graph looks like what you would have expected. The second graph is just the reflection of that around the y-axis. The third graph is going to be off of our window. So let's go back to window and go down to y min and put negative 4 for y min. And now let's do the graph again. I want you to watch that graph. You see the second one. And then when that comes down, The third one approaches the line y equals 3, but it never touches it. Okay. So we can use transformations with exponential functions also. Now, there's an exponential function that occurs so often that it has a name. It's called the natural exponential function. And this is what it looks like. It is f of x equals e to the x. And if you will go to your graphing calculator, you'll see there is an e on your graphing calculator. It's to the left of the 4, it says ln, and right above it, it says e to the x. E is a number similar to pi that occurs very, very, very often in nature, in math, and whatever. So what I want you to do, we're going to do a little exploration again. I want you to go back to y equals, clear out what you have in. Now go to y sub 1, and I want you to put y sub 1 equals e to the x. So you're going to go second ln e to the x, close parentheses, enter. Now put y sub 2 equals 2 to the x, enter. And y sub 3 equals 3 to the x, enter. Let's go to window. Let's change it back. Let's keep the x as negative 3 to 3, but where the y now said a negative 4 from our last one, put it back to negative 1 to 6, hit graph. There's e to the x. Notice it also goes through the point 0, 1. Here comes the 2 to the x that we've used, so it's on the other side of e to the x. 3 to the x is on the inside. Notice the e to the x is really, really close to the 3 to the x. So it looks like this. It's going to go through this point. Here's e to the x. Now when you do 2 to the x, it goes like this. I didn't draw that very well. But when you do 3 to the x, it's really, really, really close to the e to the x, which says e must be in between 2 and 3, closer to 3. So let's see if we can figure that out. I want you to do second quit, and now I want you to go second ln e to the, put 1, close parentheses, because e to the 1 will tell us what it's equal to. And look, it's equal to 2.718281828. So it is close to 3. But they all still go through the point 0, 1. Let's go to example 4. It says graph f of x equals negative e to the x minus 3, where x minus 3 is your exponent, and it says using transformations. Determine the domain and range and horizontal asymptote, which, by the way, I don't think we did the domain and range on the last one, on example 3. We didn't do the domain and range, so we will have to do that. All right, let's start with the parent function, which is just f of x, or y, equals e to the x. So we know that it looks like this, and it goes through the point 0, 1. All right, we know that. All right, secondly, we are going to deal with this, that negative sign, before we do the one above. And that negative sign is saying the whole y becomes negative. So what we're going to do is take this function and it's going to flip across the x-axis. So our second graph is going to look like this. Instead of it going through 0, 1, it now has to go through 0, negative 1, and picture this whole thing flipping across. It's going to look about like that. It flipped across the x-axis. So this is the function f of x equals the opposite of e to the x. And now let's look at the last piece that we have. And it says, we're going to deal with this. Notice we're doing something to the x. We are taking away 3 within its position, which was within its exponent. That is a right horizontal shift of 3. So instead of going through the point 0, -1, it's going to move over and it's going to go through the point 3, -1. So it's going to go here and it's going to go like that. So it's this same graph shifted over. So this is f of x equals negative e to the x minus 3. Now I want you to try to put that in your calculator and take a look at it. So go into y equals, clear, go to your parent function, y equals second e to the x, close your parentheses, hit enter, go to y sub 2, and we're going to do the opposite. So the negative sign, negative second e to the x. All right, hit enter. And then finally, y sub 3, you're going to have negative second e, oops, I hit the wrong thing, e to the, now within the parentheses of x, you're going to go x take away 3, close parentheses. And we're going to have to change our window. So let's change our window. 1, 2, 3, 4, 5, 6, 7, 8. Let's do y. Let's leave the x's as negative 3 to 3. No, let's change x's to negative 4 to 4, scale of 1. Let's do y's negative 8 to 8, scale of 1. And now hit graph. There's your first one. Goes through the point 0, 1. Here comes your second one. It goes through the point. See, it's reflected right across. It's actually easier to see it by doing it on the same set of coordinate axes. And then it moves over. I think that's easier to see than the way I did it. So I hope you're looking at your graphing calculator there. Now let's talk about the domain. And this domain part is true for example number 3 too. So I'm going to kind of do them at the same time. The domain, what can x be? Well, x can be anything. Notice it goes to the left to negative infinity, and it goes to the right to positive infinity. So the domain is negative infinity to positive infinity. The range on this one, however, and I'm talking about the range of the final function, what is the lowest that y can be? Well, it continues to go down, doesn't it? So y can be negative infinity. However, in the up direction, what does it approach? It approaches the x-axis. So it approaches 0, but it never reaches it. So that this equation, y equals 0, is a horizontal asymptote, meaning it gets near it, but it never touches it. So when you go back to example number 3, where we were supposed to find domain and range, and we didn't, the domain here, domain, same thing. Our x can be negative infinity to infinity. Our range, however, of our final function, the lowest that it goes, it approaches this line, y equals negative 3, but it never touches it. So the range is negative 3. How high can it go? It continues up, so it goes to infinity. There is a horizontal asymptote again at y equals negative 3. You're going to see that exponential functions have a horizontal asymptote always, what they approach but don't touch. For the last part of this section, we're going to look at exponential equations, and we're going to do quite a bit of this. In fact, we're going to come back to this later and do an entire section on it. But if you will look about halfway down your notes, it says solve exponential equations, and you see something that says if a to the u equals a to the v, then u equals v. Now what does that mean? It means if you have the same base raised to two different exponents, then those two exponents must be equal to each other. So for example, if you had 2 to the 4th equals 2 to the 3 plus 1, because those bases are the same, that we could say that 4 equals 3 plus 1. And we know that that's true, and that's a very simplified version of this. But how can we use that to solve exponential equations? Well, let's take a look. We've got 3 to the x plus 1 equals 81. Are the bases alike? No, they're not. So we have to get them alike. Well, is 81 one of the powers of 3? 3 to the first is 3. 3 squared is 9. 3 cubed is 27. But 3 to the fourth is 81. So I can make the bases be alike. So what I say is 3 to the x plus 1, now I'm going to rewrite 81 with the same base, is 3 to the fourth. Now that the bases are the same, I use this rule and I can say, therefore, x plus 1 equals 4, and that is a very easy equation to solve, and I get x equals 3. And that is true. But you must have the bases the same. So let's look at example 6. Here we have e to the negative x squared equals e to the x, the whole thing squared, times 1 over e to the third. Now it's hard to see what you've got here, and I know you're not used to using e yet, but it works just like any other number or base. So what we're going to do is we're going to say e to the negative x squared equals, now I got to deal with this side. So what is that side? So just that one side is, here it's the power rule, e to the 2x times 1 over e to the third is the same as e to the 2x, e to the negative 3. Remember, I can move it and make it negative, unlike what we normally do when we move it and make it positive. And so that is the same as e to the 2x minus 3. You've got to know your exponent rules here. So I'm going to go back to where I started. E to the negative x squared equals e to the 2x minus 3. Now, why did I have to go through all that? Because I want my bases to match. Therefore, now that they do, negative x squared is equal to 2x minus 3. All right, I'm going to add an x squared to both sides, and I end up with 0 equals x squared plus 2x minus 3. And now we're going to be back to, I have to factor that. What are factors of negative 3 that combine to make positive 2? That would be 3 and negative 1. 3 and negative 1. So I have x plus 3 times x minus 1 equals 0. So either x plus 3 equals 0 or x minus 1 equals 0. X is negative 3 or x is 1. Did we solve the equation? Yes, we did, but we got 2 answers. So our solutions are negative 3 and 1. But again, you wouldn't be able to do that if you couldn't figure out this right-hand side and get it to be the same base as the left-hand side. So those can be kind of tricky. All right, let's look at an application problem with exponents. There's lots and lots of them, particularly in science, but let's look at this one. Example 7, it says, between 9 p.m. and 10 p.m., cars arrive at Burger King's drive-thru at the rate of 12 cars per hour, or 0.2 cars per minute. The following formula from statistics can be used to determine the probability that a car will arrive within a certain number of minutes, called t, of 9 o'clock. So 2 minutes after 9 or 5 minutes after 9, whatever. So we have this formula. F of t equals 1 minus e to the negative 0.2t. Looks like that. So part A, determine the probability that a car will arrive within 5 minutes of 9 p.m. So that is that a car will get there before 9:05. So the question really is, what is f of 5? So we can just put a 5 in, a 5 here and a 5 here. So we have f of 5 equals 1 minus e to the negative 0.2 times 5. All right, now we're going to put it in your calculator, and you're going to have to learn to do this and be very careful. So in your calculator, you're going to go 1, take away, second, ln, which is e, 2, then notice it's in parentheses. So we want this all in parentheses. Now use the negative sign, 0.2 times 5, close parentheses, hit enter. And what you should get, f of 5 is approximately 0.63212, and it keeps going. So if I show that decimal as a percent, I would say you have a 63% chance of a car arriving, going through the drive-thru before 9:05. Pretty good chance of a car going through, 63%. And that's how it works. You're just plugging numbers into the formula. All right? Let's look at B. It says determine the probability that a car will arrive within 30 minutes of 9 p.m. In other words, before 9:30. Well, I would think that would be a really high probability. So now we want f of 30. We're going to do, 30. We're going to do the same thing. 1 minus e to the negative 0.2 times 30. Put that in your calculator, and you're going to get f of 30 is approximately 0.9975. So I'm going to say 99.75% chance of a car arriving before 9:30, which makes sense. I think you would expect that. Okay? So then C is an interesting question. It says, what value does f approach as t becomes unbounded in the positive directions? Well, first off, what does that mean? It means if I keep making this t bigger and bigger, 30 minutes, and then 40 minutes, and then 50 minutes, and then 60 minutes, and et cetera, what is happening to my percentage? It is approaching... It approaches 100%. Does it ever reach 100%? No, it does not, because there are circumstances that could keep that from happening. It would be very rare, but it doesn't ever reach it. Finally, it says graph f using your graphing calculator. I'm going to give you the window, and then you are just going to type in this function, and we're going to sketch it. So I want your x min to be 0, the max to be 30, and I want the scale, x scale, to be 10. And then your y min is 0, sorry. Y max is 1, because we're only talking about an hour here. And your y scale is 0.2. That's kind of a different window. Now I'm going to give you some time. I want you to go in. These are the minutes down here. That's our x, or our t. So we have 0, 10, 20, 30, and it's going to keep going. 10, 20, 30. And then these are the percents over here. So go into your calculator. Y equals, clear out what's there, go up to y sub 1, and I want you to type in 1, take away second e raised to the negative 0.2x. We're going to have to change it, the t to an x. Close parentheses. Let's go to our window, and let's go ahead and type in 0, 30 with a scale of 10. Your y min is 0, your y max is 1, which is 100%, and the scale is 0.2. Hit graph. And you're going to see that it looks like this. It approaches 100%. Doesn't ever get there, but it does approach it. All right, there's a summary in your textbook on page 432 about exponential functions. Plus, I gave you one in class, the summary of f of x equals a to the x. and I did it in 2 columns when a was a whole number greater than 1 and when a was a fraction. I want you to take a look at that. The first things are identical: the domain, the range, the x-intercept, the y-intercept. The horizontal asymptotes is where it becomes different. And then look at some other things I have there, and then the points that it passes through, and then I did a sketch. So I want you to look at those. I'm not going to draw all that on here.